The next topic we are going to see in this chapter is fundamental theorem of arithmetic. Fundamental theorem of arithmetic. What exactly this theorem talks about? Nothing new, big name. Actually, you studied in the lower classes how to prime factorize a number. Means you are dividing a number by prime factors. Prime factors again and again until it becomes 1. No prime factor left out. Let us see this example. This 2100. I divide by 5. I got 420. Again dividing by 2, by 3, by 2, by 7, by 5. All this when I divide, finally the number becomes 1. Means I am only using prime number for dividing. Prime numbers. Later I write the given number as a product of all those devices, factors, like this. This is prime factorization of 2100, expressing the given number as a product of its prime factors. Okay, only prime number used for dividing. Okay, this is something about it. What the theorem says exactly about it? Every composite number, composite number means having more than 2 factors. Prime number has exactly 2 factors. These numbers have more devices other than the 1 and the number itself. Such numbers are composite number. Every composite number can be expressed or factorized as a product of primes, product of prime numbers. And this factorization is unique, only one way, apart from the order in which the prime factors occur. Means the prime factor can occur in different way, different order, but those factors will be exactly the same, whatever the order in which they are coming. See this example, 2100. I first divide by 2, I got this. Then again I divide by 2, I got this. Then by 5, again by 5, then by 3, then by 7. Then when I write the prime factor, see the order. 2100 is equal to 2 into 2 into 5 into 5 into 3 into 7. Usually we write in the power notation form. Twice we get 2, so we are writing 2 power 2, like that 5 power 2 into 3 into 7. This order. This is a normal order. Okay. Now the same number I take, as I told you before, instead of starting to divide by smallest prime number 2, then I use 5 first. Why not? I think 5 will divide, so 5 I start with. I got 420. Now I divide with 2. Got 210. Again divide by 3. 70. Again divide by 2. In different prime factors I am using. Then by 7. Then by 5. So this time I got 5 into 2 into 3 into 2 into 7 into 5. See these prime factors taking place here and see these. Is there any difference? All are same, exactly the same factors. But the order in which, apart from the order in which the prime factor occur, different order. Here 2 comes first, here 5 comes first. No matter. But exactly the same number of times all the factors occur. Here 2 comes twice, 5 comes twice, 3 once, 7 once. Same way here also. 2 comes twice, and 5 comes twice, 7 once, and 3 once. So the order is 5 square into 2 square into 3 into 7. Exactly the same. Only the order I wrote in different. In the same manner, instead of starting to divide by 5, you can start dividing by 7, no matter. But again you are going to get exactly the same factors in the same number of times, each one coming. So prime factors won't differ exactly. This is what here we say, prime factorization is unique, only one. There is no other new factor you will find out. Exactly the same factor for any composite number. This result is called fundamental theorem of arithmetic. Let's write down and let us go to these few examples from our question in the book. This question just only talking about write the prime factorization of the number. This you are studying from lower classes even. So I have written the numbers from your textbook. 140, write the prime factorization. 156, 5005. These three questions you do at home. Okay, just write like this one I have done. This power notation form only you write. And here I wrote one question for you. 7429, because this is not divisible by any prime number. The smallest prime number is 17. So if 17 you divide, you got this number. Then only 19 will divide. Then 23. 23 also prime number. 23 will divide. So 7429 is 17 into 19 into 23. Right? You do these three by yourself. Yes. Now here is other method. HCF and LCM. LCM we have not discussed in the chapter so far, and you are already very familiar with the least common multiple LCM. HCF and LCM by prime factorization method. By prime factorization. Just now you have seen example how to prime factorize a number. So by prime factorization method. Here we write some definition. There are many methods, but as per our textbook method, by prime factor method means we follow this one. HCF of two numbers, positive integers, A and B, I take two numbers A and B, is the product of smallest power of each common prime factor involved in the number. Okay, with an example it will be more clear. Product of smallest power of each common prime factor involved in the two numbers. Okay, let us come to LCM. LCM of the numbers, product of greatest power of each prime factor involved in the number. Here they don't talk about common. All prime factors you are taking and take the highest power of each variety involved in the two numbers. Take them and multiply them. That is LCM. This is what this definition. So product of greatest power of each prime factor involved in the number. If these letters are not clear, you can copy that from page number 10. In your textbook it is given in bold letters. Copy from there. To know clearly about the given statement here, we have taken this example. Find the HCF and LCM applying prime factorization method. Applying prime factorization method. So what we do, we are given two numbers, 126, 600. The prime factor method, we are writing what is the prime factorization of 126. It is 2. 2 to the power 1 I wrote in power notation. 2 into 3 square into 7. 7 power 1 I wrote. Don't mind. 7 power 1 is 7. Prime factorization of the 600. That is here 2 cube into 3 power 1 into 5 square. These two prime factors are made ready. Now when I am writing about what is FCF, now come back to this. FCF is product of smallest power of each common prime factor. Okay, now I am seeing what are common in it. Here, common, 2 power 1, 2 power 3. And here 3 square, these 3's are common. And here 5, 7 are not in common. Among these two 2's, I take the smaller power. Means 2 power 1. Okay, 2. In these two, what I have to take? The smaller power, smallest power they say 3 power 1. So 3 I have to take. I should not take 3 square. So among the common prime factors, among 2's, I take 2. 2 power 1. And among the 3's, I take 3. 3 power 1. So this 2 and 3. 2 power 1 into 3 power 1. multiplied HCF is 6. Now you will understand that definition clearly. Let's come to LCM. When I take LCM, I should not see what is common, what is not common. Collect all the varieties of prime factors we have in those two numbers. I have 2's, I have 3's, I have 7's, and I have 5's. Okay, need not be common. Among all these, I have how many varieties now? 1, 2, 3, 4 varieties. 2's are there, 3's are there, 5's are there, 7's are there. Among all these, among the 2, what is the highest power? The 2 cube I take. Among the 3's, 3 square. You have only 1 7. So 7 power 1. Here 5 square. These are all I multiplied. So I don't have to see where is common thing. I have to take highest power involved in all these factors. It's 2 cube into 3 square into 5 square into 1. This when I multiply I get 12,600. 12,600 is the LCM and 6 was the HCM. So this is the way you find out. After seeing this example, you read 2 times that definition. You will more clearly understand what it is. Product of, greatest power of, each prime factor involved in the, not common, each prime factor involved in the. Okay, let's go to this one. Now they are asking some questions here. The questions are, they will ask you, suppose 3 numbers are given, 3 numbers. These are the 3 numbers. 1,820, 2,450, 520. 3 numbers. They are asking you what is the HCF and LCM. You write prime factors of each, as we did before. They write in that order. Power notation, use 2 square like that. 2 square, 7 into 5 into 13 here. 2 into 7 square into 5 square here. 2 cube into 13 into 5. All we wrote. Go for HCF. HCF what are common here? It should be common in all the 3 sets, not in 2 sets. All the 3 sets. Okay. Let's take here 2's. Among the 2's common in all the 3 sets. The lowest power is only 2 power 1. Here 2 square, 2 power 1, 2 cube. So 2 power 1 is the lowest power. That I take 2. Here 5 square, 5. So lower power is 5. So the 2 and 5, you multiply 2 into 5, HCF is 10. Okay. Then go to LCM. LCM, as I told you, you don't have to see where is common or not common. You have to take out one more thing here. In HCF while I am finding, see 7 is involved in these 2 sets, but not in the third number. So you should not take 7 there. It should be in all the 3 sets. Then only common. Okay. Like that here also, where we have this 13 here, as well as the first number. So I am not taking 13 when I calculate HCF. But while calculating LCM, I don't see where it is common or not. I take highest power of all varieties of prime factors available in all these 3 numbers. So I check all the 2's, 2 cube highest, take 2 cube, and check the 5's, 5 square highest, take it, 7. It need not be in all the 3, 7 is here and here, no matter. So 7 square I take. Only 2 13s, here 1 13, here 1 13. But highest power of 13 involved in them, 13 power 1, so 13. These are all you multiply. So you get what? 1,27,400. This is the LCM. So HCF is 10, LCM is 1,27,400. This is when you are calculating with the 3 numbers. Okay.